if you at some point today is definitely the toughest lecture of the semester, so don't worry if you start getting a little bit lost. Try to come back in at a different part. There's a couple different parts where you can kind of get back in and probably be okay. I think the only really horrible stuff comes at the very end in any event, okay, where it gets really complicated. So the easier stuff comes first, harder stuff comes later. I forgot to say that we're only going to cover tuple relational calculus. We're not covering domain relational calculus. So if you found the domain relational calculus stuff pretty complicated, it is definitely tougher than tuple relational calculus. And SQL is based on the tuple relational calculus. Okay, so the relational algebra and relational calculus form what's called the theoretical basis for data manipulation languages in relational databases. SQL is based on the relational calculus. Okay, so our second lecture of the semester, we talked about the formal basis for the structure of a database, the DDL. The relational algebra and relational calculus provide the formal basis for the query language, for the DML. Okay, so we'll talk about what is meant by relational completeness, how we form queries in the relational algebra, and how we form queries in the tuple relational calculus. So again, both the relational algebra and relational calculus are formal theoretical languages. They're not actually implemented anywhere. The relational algebra is a high-level procedural language. And essentially, it was meant to be something that a query optimizer could convert a query into relational algebra operations and then optimize based on those relational algebra operations. So think of it as a high-level pseudocode, and it's procedural. In contrast, the relational calculus is declarative and non-procedural. The relational algebra is a precise recipe for how to perform a query. The relational calculus is not. It simply says, this is what I want, but it doesn't tell you how to go about getting it from the database. It leaves it up to the query optimizer to figure out the best way to do it. The two languages are formally equivalent to one another, but when we talk about relationally complete, we are talking about the relational calculus, not the relational algebra. So if you want what is truly the formal basis, the true formal basis, it would be the relational calculus. So on the quiz today, one of the questions says, are the relational algebra and relational calculus the formal basis? The answer is yes, they are. You should check it. But when we talk about when we come up with a query language like SQL, and we want to know whether it faithfully implements all possible query features in the relational model, we are asking whether it is able to derive all operations that are derivable from the relational calculus. So we say that a language is relationally complete if essentially it can implement all queries that can be implemented using the relational calculus. So the relational calculus is what actually forms the basis for SQL. The relational algebra is more or less a high-level pseudocode that the query optimizer uses to convert SQL to a high-level pseudocode that it can then do query optimization on. Relational algebra is easier to deal with, so we'll cover it first. Okay? So it is, we'll come back to this in a moment. Let's first talk about the basic operations. So remember I said select, project, join. Those are the basic operations in your query language. You'll notice that it is not, join is not one of the 5 fundamental operations in the relational algebra. It's selection and projection, something called the Cartesian product, set union, and set difference. Then there are 3 convenience operations that are added, which are the join, the set intersection, and set division. And the reason they're not part of the basic operations is they're derivable from those 5 basic operations. So basically, they try to keep the basic operations to exactly those operations that are irreducible. Join, intersect, and division are reducible in the sense that they can be expressed using some combination of those 5 operations. So join can be implemented as a selection on a Cartesian product. Okay, and we'll show you how the other 2 operations can be implemented. Okay, so now what a relational algebra operation does is it produces another relation. So what it does is it operates on one or more relations, and the result is itself a relation. It's a new relation. The original relations are not modified. So you get a new relation. That new relation can be piped into some other relational algebra expression. So just like in a arithmetic, you're allowed to write something like A plus B times C. You can do the same thing with relational algebra operations. You could have some kind of relational algebra. You don't yet know what these things are, but you could say okay, so this is actually in the relational algebra, this is called a join or a Cartesian product. Actually, let me do, instead of that, let me do an X. So that's the Cartesian product. That produces a relation, which you can then perform a select operation on. So just like in arithmetic, you can have nested operations. You can have nested operations in the relational algebra because the result of each operation is itself a relation. Okay, and that operation is called, that property is called closure, that every operation produces a relation. Okay, so you're pretty familiar with selection, projection. Cartesian product, I'll cover it in case you're not sure about it. You should know what union and set difference, intersection, and joins are. The only 2 that you really don't probably know are set division, possibly Cartesian product. So Cartesian product, you can see here, you simply take every tuple in the first relation, concatenate it with every tuple in the second relation. So here A1, A2, and A3 is what you get from concatenating A with each of the tuples in Q, and then B1, B2, and B3 are what you get from concatenating B with every tuple in Q. Okay? Set division is the one that is nastier. Okay, so before I show it to you, let me just tell you what kinds of operations involve set division. Let's say that I'm the Tennessee Parks Association and I want to recognize all tourists who have visited every park in Tennessee. Okay? So what I'm looking to do is whomever has visited every park in Tennessee, I want to recognize them. I would use set division to locate the tourists who have visited every park in Tennessee. So, let's say in a hotel, I'd like to know which guests have stayed in every room at a hotel. Okay, so which guests have stayed at every room in a hotel? I'd use set division for that. Okay, so let's see what it looks like in practice. So here I have a relation V. It has two columns A and B, and I have a second relation W. Okay, let's put this in terms of what I just said. Let's say that W is my parks in Tennessee. So let's say I have Park 1 and Park 2. And let's say that V is a list of all visits. So this A is the tourist name and B is the park they visited. So this is a list. V is all visits by tourists. So tourist A visited Park 1, tourist A visited Park 2. Tourist B visited Park 1 and Park 2. Tourist C visited Park 1. So when I do my division, what I said is I want all tourists who visited all the parks in Tennessee. Well, if you look here, A has visited all the parks in Tennessee, and B has visited all the parks in Tennessee. So the result of the division is A and B. Okay? So it is what you have is the divisor is some subset of the columns in the dividend. The remaining columns, in this case A, are the columns that appear in the result. So the columns that are in the divisor do not appear in the result. It's only the columns that are not part of the divisor that appear in the result. And in order to appear in the result, you must match your remaining columns, in this case A, must match all tuples in your divisor. So think of it as a more severe join. Okay, with a join, if I were joining V with W, then it would be enough since 1 matches 1, this tuple would appear in the result because it matched one of the columns in B. In essence, we're now saying the only way you show up in the result is you can't just match one column, you have to match all columns. So C doesn't show up in the result because while it matches on 1, it doesn't match on 2. Okay? So we say that in this division, the remainder is C1. Okay? And the result is A and B. The remainder is whatever doesn't make it into the result. So that's set division. Yes?
If there was inside of V, if there was like A3, but 3 was included in W, would A still be included?
Yes, A would still be. So the question was if there was an extraneous tuple in V like A3, would it still appear in the result? And the answer is yes. So to show how your example might apply, let's say that actually this is a database, V, is a table of visits to all 50 states. Okay? So it might be that A also visited some parks in Georgia or Kentucky. We don't care about that. We only care about the fact that they visited all parks in Tennessee. So, good question. Okay, so set division takes a little bit of time to wrap your head around it, and the book does, or my handout, which was from the original book for this course, doesn't, in my opinion, give you a good feel for what set division is. As I said, set division is basically about finding all entities that who have visited all of something, all instances of something. Okay? Okay, so you're going to get introduced to some other types of joins. We will get to that in a moment. Okay, so I'm going to go through the next set of slides quickly because all it's talking about is notation, and you should have been able to read that in the book. It's pretty simple. Selection on a relation, so you put the relation in parentheses. You have this, I think it's sigma with a predicate. So for example, if I want all staff whose salary is greater than 10,000, you use the selection. To do projection, it is the capital Pi with the comma-separated list of columns. So here we want all staff numbers, all staff. We want the column staff number, first name, last name, and salary from staff. So we use capital P. Now, let's say we wanted to combine this. Let's say we want the staff number. Let's say we want first and last name of all staff making greater than 10,000. We would write, let's select all staff whose salary is greater than 10,000. And then we would project out the first name and last name. So here's an example of nesting. We first do the selection, then we do the projection. We could reverse that. That's why it's procedural. We could have written instead, project out the first name and the last name from staff, and then take all of those whose salary is greater than 10,000. So it's procedural. It actually specifies the order in which the operations are performed, and they go inside out. So in the first one, the selection is done first, followed by the project. In the second one, the project is performed first, followed by the select. So it's procedural. The relational algebra specifies the order of operations, and that's why it comes in handy for a query optimizer. What the query optimizer essentially is doing is taking an SQL query, is translating it essentially into a relational algebra expression that gives a precise set of or sequence of operations to be performed in order to satisfy your query. Okay? Okay. We've talked about union, so I'm not going to talk about it again. Remember, it has to be union compatible. So we have to project down to two relations that have the same number of columns and the same types in each column. They don't have to have the same names, just the same types. Okay, so in fact, here is an example where the names aren't the same. See ID and property ID. Although actually I think I projected down to city in this case. Did I take? No. In fact, I was taking the union and they are union compatible, even though this name of this column and this column are different, they have the same types. Okay? In this case, I end up projecting down to the city. And originally I could project down to just one column, but in fact, with 3 columns, these are still union compatible. Now, one thing about it though is here, when I projected down, I eliminated duplicates. You'll notice that if I did a strict union, this Columbus 1678 Cardiff Road. Actually, there's no, this Knoxville 5485 Alcoa Highway. This Knoxville 2408 Trillium Lane. The IDs are different and the addresses are different, so both of these tuples would appear in the union. And in fact, there would be 9, if I'm not mistaken, there would be 9 tuples in the relation, and then when we project down, we end up with 5 because we eliminate duplicates. Okay, so here's an example again of nesting the operations. Here we project down beforehand to a city, to a single column, and then after we've gone down to a single column, we perform the union. Okay, set difference, whatever is in R but not in S. So we've already gone through examples of that, so I'm not going to bore you. Intersection, our first convenience operation. So it turns out that you can express intersection as 2 difference operations. So you may have to take a moment to think about this. So I've tried to show you with a picture. So we're taking the intersection of R and S. So here's R, this from here to here. Here's S from here to here. So the white part is their intersection, right? So I'm claiming that R intersect S is actually can be formed by taking the set difference of R and S and then again taking that set difference with R. So let's verify that fact. So the blue is whatever is in R but not in S, right? Do we agree with that? Okay. So when we now say R minus this set, it is whatever is in R but not in this set, that must be this white portion, which is R intersect S. Okay, not claiming it's completely intuitive. You may have to think a bit about it, but that's the picture. So we don't make intersection one of our basic 5. It's a convenience operation because I can get it from 2 difference operations. Test questions I love to ask. What are the basic operations that form set intersection? Or what are the basic operations that form a join? Okay, Cartesian product. Simple enough. Concatenation of every tuple of relation R with every tuple of relation S. By the way, I never said this, but if you happen to pull this stunt in SQL, let's say I say select B dot star, or let's say I say select staff dot star, branch dot star from staff branch with no where clause. That's a Cartesian product. The result that SQL gives me is a Cartesian product of staff and branch if I don't have any where clause. So if you're wondering how you get Cartesian product in SQL, you never do this, but if you did, you'd get the Cartesian product. Okay, so pretty simple. Now, joins are a Cartesian product and a selection. So here, I'm taking student Cartesian product courses. This is a join. So I'm asking for all students that match with their course they're taking, and then I project out from the result the student ID in the course. So this is giving me all students in the courses they take. So back here, I took the Cartesian product of all students and courses. Okay, coming up with this Cartesian product here, which I've repeated over here. This is the Cartesian product of student with courses. So I care about all tuples where the student IDs match. So student ID 1 took CS140 and ECE 255. That matches this student ID equals course ID. This doesn't match. Okay? Student 1 did not take CS302. That was taken by student 2, so it's not a match. Similarly, student 2 did not take CS140. That was taken by student 1. But eventually we get to student 2 did take CS302. They match. So these three come out of the selection. What you see here is a join. This right here, the combination of the selection with the Cartesian product, that is a join. So again, a join is a convenience operation. It is actually formed from a Cartesian product and a selection. Okay, it turns out to be devilishly difficult to implement efficiently. It is one reason why NoSQL has come up, because joins definitely slow down relational databases, especially when you have to join multiple tables. Okay, there are various types of joins. The most general type is the theta join. Then we have an equijoin, a natural join, an outer join, and a semi-join. You've already seen equijoins, natural joins, and outer joins. This is how we write in the relational algebra a join. It looks like a bow tie. That's how I just think of it. It's a bow tie. And the theta join specifies an operation. It can be any one of the relational operators. There's 6 of them. So for example, you could do a join of, let's see, trying to even think of something that makes sense. Okay, let's come up with, let's say that we had clients and they have a max rent they're willing to pay. And let's say we have properties for rent, and it has a rent, and for the moment I'll just say a property ID. So you could write a join of client with property, and the formula you would use might be that client dot, actually we'll write property dot rent is less than or equal to client dot max rent. So this would be a theta join where we're returning all properties for each client where the property rent is less than the client's maximum rent. So for each client, we would see all the properties that would be available. Now, normally we'd only want to see it for a single client, not all clients. That's why you rarely see a join written this way. But that's an example of a join where I'm using something other than an equal operator. Now in practice, all we care about are equals. Okay, so, and I thought I had silenced my phone, but I have not, so we have to do that. I had silenced my phone. Ah, my wife called me twice in a row. Do you know how you break, um, do you know how you break do not disturb on a phone? You call someone twice in a row, and that breaks it.
You can turn that off.
I can. That, okay. So, just a second, sorry. My wife feels it's important enough. Okay. You go to, how do you stop that? Airplane mode? How do you stop getting, if someone said you can stop it? Pardon?
If you go to the settings, you can turn it off or it won't let it bring you on.
Gotcha. Okay. Okay. Coming back. Normally we use equality with our joins. So when we use equality, we call it an equijoin. But that is simply one version of a theta join. An equijoin is a type of theta join that uses equality. Typically, we only use equality. Okay, so here's an example of an equijoin. We are doing a join of students with courses. Now notice before we do the join, we actually project it down to only ID and name and course ID and comment. Then we join the two projected relations on the equality involving their IDs. Okay? Again, I'm going fairly quickly because you should have already be comfortable with joins. Natural join, notice I don't list the columns that I am comparing. So before, there was this little formula down here, F. A natural join omits the formula because it's an equijoin on all common columns. What are columns? Columns with the same name. Okay, and we eliminate, we would ordinarily end up with two columns with the same name. We automatically eliminate one of those two columns. Okay, we've seen natural joins. Outer joins, remember that's where we want to include tuples that don't match in the other relation. So in this case, this is a left outer join. We want all tuples in R, even those that do not match the ones in S. You'll notice their bow tie is open. If I want a full outer join, it is weird because you have to put, notice the extension here. If you just took off both sides, it would look like Cartesian product. So notice there's a little extension. So if you wanted the full outer join, let's say I had client and property and I wanted the full outer join, it would look like a Cartesian product except I would extend the bow tie like that. So that right here, this is a full outer join. Okay, it's different, it's not a Cartesian product. Remember, a join is going to be all matching tuples plus those that don't match in client plus those that don't match in property. That is different than taking a Cartesian product, which would have a lot of non-matching tuples concatenated together. Okay? Now, the join you have not seen is a semi-join, but it's easy. A semi-join, notice you only got half of the bow tie now, says I only want the tuples in R that match some tuple in S. So I don't care about anything from S. I only, in my result, it's like a projection where I'm only asking for columns in R. So that's why we can rewrite the semi-join as a join involving R and S, where we project out all the attributes in R. Okay, semi-joins are actually quite common. So let's say that we want to list all the details of all students who are taking CS140. We don't care about anything in CS140 other than what students are in 140. So we start and we select from courses the one tuple that has CS140. Then we do a join and find all students taking that one course, but all we're interested in is the details of the students taking that course. So in the end, we took the join, but then we only were interested in the tuples from student. We didn't care anything about the tuples from courses. So it's called a semi-join. It's half of the bow tie, and the half that is showing is the relation we want in the result. Okay? Easy enough? Okay, set division. Denoted R divided by S. So just again, the more examples you see, the easier it'll get for you. So here we want to list all guests who have stayed in all rooms of the Grosvenor Hotel. So we'll assume that rooms 100 and 200 and 300 are the only rooms in the Grosvenor Hotel. These are bookings. We have projected away all but the guest number and room number. So you can see that guest 30 has stayed in room 200, 300, and 100. Therefore, guest 30 shows up in the result. 20 has stayed in 100 and 300, but not in 200. So that would be part of the remainder. Same thing, 10 has stayed in 100, but not 200 or 300. That would be part of the remainder. We generally don't care about the remainder. We generally only care about the quotient. How do we do division in terms of the other operations? Because we said that it's a convenience operation. It can be done by doing the other operations. Well, first of all, we have to have some preconditions. So R is defined over an attribute set A. That's the dividend. The divisor S is defined over an attribute set B that is a proper subset of A. In fact, it should be proper subset. I know here it has the underline, but really should say proper subset. The quotient will be whatever attributes are in A that are not in the divisor. So C is our quotient set. Okay, so how do we derive it? The first thing we do is we project out the quotient attribute C. So we get a relation T1 that has just the quotient attributes from R. Now we take that and we do a Cartesian product of T1 with S. So that would be, think of T1 cross S as the relation we would get if all of our guests had visited all of the rooms at the Grosvenor Hotel. Okay, so if every single guest we've ever had visited every room in the Grosvenor Hotel, that is what T1 cross S is. Now, from that, we subtract out the actual guest visits. So what we're left with, after we subtract out all the guest visits, is those guests who have not visited those rooms. Okay? Think about it. Let's look at this. Let's say this is our rooms in the Grosvenor Hotel, 1 and 2. Here's our guest visits over here. Okay? So T1 is all of our guests that we've ever had. T1 cross S would be all possible guests with all possible rooms. When we subtract out R, what we are going to be left with is whatever rooms the guests have not visited. So if we subtract R from S, we will find out the result will be C2, right? And that's it. So the remainder will be C2, and that is because C2 never visited that room. So what we're left with after we do this subtraction of R from T1 Cartesian product S is all rooms that were not visited by a guest. So now when we take the Cartesian product, when we project down, we find all guests who have not visited some room. In this case, we get C because C has not visited room 2 in the Grosvenor Hotel. So T2 is essentially all guests who have not visited all rooms. So at this point, we subtract that from our guests, and that gives us all guests who have visited all rooms, which are A and B. Again, not claiming this is easy to see. You probably need to look at this slide and digest it, but set division can be formed from these 3 basic operations. Questions? Like I said, you may have to sit down and look at this slide a little bit when the class is done, because I'm not claiming it's obvious. Okay. Back to a little bit of a relaxation for a moment. The aggregate operations are shown as, I think this is tau, and then it's an aggregate list. AL stands for aggregate list. This is how you're renaming the columns. So remember, in a select statement, you can say something like you're allowed to say something like select count star as enrollment. From maybe courses. So the comparable thing would be P of, make sure I get this right. Yep. Tau, of course I'm always so good with tau, count star courses. So that is the relational algebra expression for the SQL statement. Okay, so here's another example where we're counting property number. We're counting the number of properties where the rent is greater than 350. And we're renaming the result column my count. So my count is whatever the name is. Okay, if you want to group, then before the tau, you put your grouping attributes. And it could contain more than one if you want it. So here we are grouping on branch number. So we're finding the number of staff working in each branch and the sum of their salaries. So we're grouping on branch number, counting the staff number, comma, summing their salary on staff. We're renaming the column, so we're using branch number here. My count is renaming count staff number. My sum is the name for sum of salary. Okay, pretty simple. Just when you're doing the homework, you'll probably just want to have this set of slides handy. Okay, deep breath. We're done with the relational algebra. Again, the relational algebra is essentially a high-level pseudocode that query optimizers use when they convert SQL queries into an action plan. So the relational algebra procedural, it specifies the exact order of operations. So it's like a plan, a query plan. Relational calculus, by contrast, is declarative. It is not specifying an order of operations. It simply specifies what we want. Okay? It is based on the predicate calculus. Okay? So what you're doing is you're specifying a predicate, which is a where clause. Before you get all bent out of shape, in SQL, a where clause is a predicate. And what we're doing is for each tuple, we're substituting the values for that tuple into the predicate, making it what is called a proposition. That proposition is either true or false. And we take all propositions that are true. So let me give you an example. Here is a predicate. S.salary is greater than 10,000. So we want the set of all S such that S is in the staff relation, is a tuple in the staff relation, and when we fill in for that staff member as salary, it's greater than 10,000. So this proposition, or this predicate, is false for any salary less than 10,000. True for any salary greater than 10,000. So we take all tuples where they make this predicate true. Okay? So we call S a tuple variable. It ranges over every tuple in staff. In SQL, you're allowed to say select staff S. Okay, so that makes it a tuple variable in effect. Anything that goes on the left-hand side is the attributes we want. In this case, we want all attributes in S. Here, we only want the salary attribute. So the only column we would get in the result would be salary. So on the left-hand side, we have the projection. On the right-hand side, we have our tuple variables and our filter, which is a predicate. Okay, this caret is an AND operation. Okay, so what we care about, we're only going to care about the tuple relational calculus. That's what SQL is based on. You don't need to know the domain relational calculus for this class. So again, a tuple variable ranges over a named relation. So in this case, the tuple variable is S. It is ranging over the relation staff. When we specify a predicate, this is how we do it. We use set notation. We are saying we want the set of all S that satisfy this predicate on S, that make the proposition true. Okay? So here's a more complicated one. And in general, what I tell you, if you have trouble writing a relational calculus query, write an SQL query for it and then translate it. So here, we want to find the salaries of all staff earning more than 10,000 pounds. So the SQL query would be select staff number and salary from staff S where the salary is greater than 10,000. Well, this is in the relational calculus. This from, each thing in the from statement is a tuple variable. So here, this gets translated down to a tuple variable. Everything in the select statement ends up on the left-hand side of this bar. And whatever in the where clause is and it with the tuple variables. Okay, so basically you and whatever is in your where clause with your tuple variables. And everything in your select statement goes on the left-hand side of the bar. Okay? Questions about that? Okay. Now, let's go through how we get some of the relational algebra expressions in the relational calculus. So if you want the Cartesian product, it is R comma S, where you have T1 going over all variables in R, and it with T2 going over all variables in S. Remember, I told you that Cartesian product was select staff dot star branch dot star from staff branch. That was the SQL, right? That's pretty much what we have here, just anding them together. Okay, how do we do a join? Okay, R comma S. We have tuple variables over R and S, and in this case, we are doing the equijoin over their common column B. That's a join. Okay, let's keep. Okay, before we do more relational algebra operations, we need to know about the there exists and for all quantifiers. So there exists means it's much like an OR operation. If there is a single tuple in the relation that matches, then it's true. For all is the opposite. It means and. Means every tuple has to match the predicate. So it's only true if the predicate is true for every single tuple. We talk about bound and free variables. Bound variables are ones that are going to be bound to a for all or there exist. Free variables are ones that are not. Only free variables can appear to the left of the bars. Okay, so here's an example. This is a semi-join example. We are finding all staff who work in a London branch. We only care about the staff, so that's all that appears on the left-hand side. The staff is a free variable. The branch is a bound variable. So staff and there exists a branch B such that B is in the branch and the branch numbers match and the branch city is London. Notice that in SQL, this can be done with a join, but it could also be done as a subquery. Right? This, if you could translate this directly into a SQL subquery. So when you see subqueries, they are based on the relational calculus. Okay, here's an example of the universe, the for all. So we want all, this thing is only true if we don't have a branch in Paris. So maybe we are having a general constraint that we cannot have a branch in Paris. We would express our constraint as for all B, B is in branch, and B dot city cannot be in Paris. Okay, and remember De Morgan's laws. So I'm not sure this is exactly De Morgan's laws, but you can take for all and make it into there does not exist. Okay, so it means that the same thing as saying for all B, there is not a branch, the branch city is not Paris. We could say there does not exist a branch such that the city is equal to Paris. So you can always turn a for all into a there does not exist. So let me just show that. We can always say that a for all is equal to a does not exist. And for a, actually, that's how it's written. And a there exists is equal to a not for all. Okay? Which is generally easier for people to deal with? Nots or direct statements? Direct statements. People don't deal well with nots. So in general, use for all or there exists if possible rather than not, because people generally don't do well with indirect statements. Okay. So remember, we are writing our predicates. Predicates are formulas. Okay, so this slide, whoops, that you cannot see. This slide simply talks about how we can build up our predicates. So anything involving a tuple variable is a legitimate formula. So if I just do select star, let's say I write select star from staff. Okay, that essentially is S staff S. Okay, so staff S in this case is my predicate. It is well formed. Okay, I can have anything that involves a comparison of two attributes where this is a relational operator or a Boolean operator, and I can compare attributes to constants. Then I can recursively build up formulas using the Boolean operators and, or, and negation. Or I can turn a free variable into a bound variable by saying there exists or for all. So if I have a formula with a free variable, I can put a there exists or a for all in front of it and turn it into a bound variable. Okay, so just again to give you an idea of how these things map back into SQL or the relational algebra, the Boolean operations are typically used for simple where or select queries. There exists X is used for semi-joins, and there does not exist and for all are used for integrity constraints. So we might say all staff members must make less than 100,000. That would use a for all. Okay, or there does not exist a staff member who manages more than 100 properties. Now, let me come back to what makes more sense to say. There does not all staff members must manage fewer than 100 properties, or there does not exist a staff member who manages more than 100 properties. This example here, this is a double negation. It is much clearer to say all staff members manage fewer than 100 properties. It's two direct statements. All staff members manage fewer than 100 properties. This is not, does not exist, and you say more than 100 properties. That's indirect. Okay? So try not to say it this way. It's just doesn't roll. People find it harder to say. Okay. Coming back to our relational algebra and how we say things in the relational calculus, if we want to do union of B and P, it is the set of cities such that there exists a B in the branch where B dot city equals T dot city, or there exists a property and the property dot city equals T dot city. Notice there is no tuple variable involving T because T, there is no such tuple. It's being formed from the disjunction of all the tuples in B and all the tuples in P. Okay, if we're doing set difference, here we're doing all cities in B but not in P. So we only care about the cities in B such that the city is in branch B and there does not exist a property P such that B dot city equals P dot city. So if we find that there is a city in P that equals the city in B, then we do not want it in our set difference. Okay, intersection is a join. In particular, intersection is a semi-join. So it is simply the set of cities in B such that B is in a branch and there exists a property P such that B city is equal to P city. So intersection is a semi-join. Set division is nasty. So consider again our parks. We want all tourists who have visited all parks in Tennessee. So we want the set of all tourists where T is in tourists and for all parks in P. Remember earlier you asked what if we have extraneous tuples? That's covered right here. So if the park is not in the state of Tennessee, we don't care about it. So we say, and either this park is not in Tennessee, in which case we don't care, or if the park is in Tennessee, then there exists a visit such that the tourist name is equal to the tourist name in the visit. And also, we have that the park name in the visit is equal to that park name. So basically, either the park is not in the state of Tennessee, or there has been a visit by that tourist to that park. There's a homework problem that involves set division. It's in the slides. Okay, here's a left outer join. So we want all students and the courses they are taking, and we want to include students in the result even if they are not taking the course. So we want all students and the courses they're taking, and the student is in S and in E, and the ID is equal to E dot, needs to say student ID. Okay, but we don't want just the students in the join. We also want students that don't match, which is set difference. So the second one is simply set difference, or the set of students S, where there does not exist a tuple in the enrollment such that the IDs match. So the outer join, the left outer join, is essentially a join ORed with a set difference. Make sense? Not claiming it's easy. You may have to think about some of this stuff when you're done. Okay. We are pretty much, take a deep breath. We're over the hard stuff. I've got some examples and we'll wrap up. Okay? So, here's a few examples. We want the names of all managers who earn more than 25,000 pounds. So it is first name and last name, staff S, and the position is manager, and the salary is greater than 25,000. Okay, here we want to list the staff who manage the properties for rent in Glasgow. If you have trouble, well, in this case, you might or might not be able to write out the SQL. So it's a semi-join. It's all staff S, and there exists a property such that the staff number is equal to that staff member's staff number, and the property is in Glasgow. Okay, here's the comparable SQL query. It's a subquery. Okay, select S dot star from staff where exists. Does anyone remember what kind of subquery this is called? It's a row subquery because it's returning a complete table. Row subqueries are ones that return a complete table with multiple columns. A table subquery would return a single column table. A row subquery returns a multiple row. Okay, now, this one will get you. You might want to write this query right here as this way, which is a join. So we're joining the staff and property for rent, and we're doing it on an equijoin on the staff numbers, and the city is equal to Glasgow. In fact, you could write this as a natural join in SQL. You do this on a test or on the homework and you will be marked wrong. Okay? The reason you will be marked wrong is because of this right here. Yes, we're doing a join, but the problem is P does not appear on the left side. So free variables must appear on the left side. They must. But right here, P does not appear on the left side, making this a ill-formed relational calculus query. This is wrong. Okay? So you have to write it this way because P is not appearing on the left side, therefore you have to bind it. Don't fall into this mistake on the homework because it's easy to do. You could easily try to write this query as a join in SQL, but the only problem with writing it as a join is that P is not appearing on the left-hand side. Okay? Here is a fine join. We want to list each property that rents for more than $450 and list the name of the staff member who manages it. So we want all details about the property and the person who manages it. Now it's okay to have both of these as free variables because they both appear on the left-hand side. Here's the equijoin, and the property for rent is greater than $450. Here's the corresponding query in SQL. Okay, so now we want to list the names of staff who do not manage any properties. So I did use negation here because it's kind of the way I stated the query. So I want the names of all staff such that the staff does not manage a property, meaning there does not exist a property such that the staff member manages it. Okay, I could have said, and for all properties, S.staff number is not equal to P.staff number. That would work equally well. Okay, and that's what this query right here is saying. And finally, a very complicated one. List the names of clients who have viewed a property for rent in Glasgow. So I only care about the names of clients, making it a semi-join. So it's important that you recognize it's a semi-join and follow the template for a semi-join, which means you're going to have bound variables for the visits and property relations. So there is a tuple in the viewing relation and a tuple in the property for rent relation such that the client has viewed the property and the property matches a property whose city is equal to Glasgow. Okay. Finally, last thing. We have to be careful about writing so-called safe queries. Unsafe queries return an infinite set. So this is an example of an unsafe query. We're asking for all staff such that the staff is not in S. Well, that's effectively anyone not employed by our company. It's in effect an infinite set. So we add a restriction that the values must be values in the domain. So in this case, the result would have to be staff that we employ. So this would return what? If it must include staff that we employ, this query returns no longer an infinite set, but the only tuples. So what we're saying is we're adding a restriction that the tuples returned must lie within the domain of, must lie. It has to include tuples only from the relations that are in our predicate. So this is going to be equal to, is there any tuple that in the staff relation that matches this? So it's the empty set. By adding this restriction, this goes from being an infinite set to the empty set. Because the only tuples allowed are tuples from S. No tuple from S matches this predicate. Therefore, this becomes the empty set, and it makes it safe. Okay, I'm not going to worry about safety, but that did appear in the book, so I just wanted to add it. Okay, I know this is a lot to absorb. When you're doing the homework assignment 3, I know homework 3 isn't assigned for another couple of days, but when you're doing homework 3, make sure that's homework 3. Yeah, so when you do homework 3, make sure you refer back to my slides. I think my slides provide more information than the handout. Okay? I think they're easier to understand as well. Okay, I will see you all Thursday. Things get easier on Thursday.